Hi, everyone. Thanks for joining us today for a 30-minute conversation with John Carrier titled Unlocking the Strategic Power of Industrial AI, hosted by MIT Sloan Executive Education. I'm Diane Abbott, an Associate Director with Sloan Executive Education. Today, I'm joined by John, who is a Senior Lecturer of System Dynamics at the MIT Sloan School of Management. John instructs senior managers on improving manufacturing and business processes and is an on-site coach in support of projects. His research focuses on strategic marketing and new business development in specialty chemicals and service segments. John has more than 15 years of experience in a variety of corporate, entrepreneurial, and consulting environments. While John is speaking, I'll be monitoring the questions added to the comments section to discuss as time allows. Welcome, John.
Thank you, Diane. And I'd also like to welcome everyone who joined us today. This is a tremendous topic because industrial AI is a very exciting new topic. Yet when we look at industrial revolutions, it really stretches over several hundred years. And we are still on this exciting curve of how do we produce more quickly, more safely, and actually create work environments that reward the people for their creativity and their dedication. And if you join this call, it certainly shows that you have interest in industrial AI and Industry 4.0. So there's really two parts to it. There's all the exciting new technologies, and then there's also all the fundamental principles of industry, of moving assembly lines and production that will never change, right? Managing and controlling systems. So that's why I subtitled today's talk, Back to the Future, because as you go to implement your new digital transformation, a deep understanding of control concepts and system dynamics that basically comes out of MIT, as well as some your experience on the factory floor, will really help you accelerate your adoption and avoid those critical mistakes that slow you down. So again, in my background, I'm a control systems engineer by training, but I spent about half my time out on operations and manufacturing floors making improvements. And one thing that we all know is companies that don't adopt new technologies will at some point just fade away. However, some of the companies that do adopt the new technologies also get into trouble, particularly financial operational problems. That's when people like me usually get called in. So as part of what we're going to talk about is how do you actually buy and implement technology so that we don't end up paying for it later and we start seeing short-term results that also support our long-term strategy. And again, using the principles of system dynamics, there is a better way. And not only are we going to talk about a framework to do that, we're also going to show specific examples of how it's done. So for today, I just wanted to present a few lessons to keep in mind as you go through your digital transformation. And these are some of the common mistakes or misgivings or missed opportunities in preparation that could really accelerate your journey. And the first one I want to show is, we're in an era where you could collect data through spreadsheets, through the web, hundreds of sensors, and put up beautiful dashboards, and that is fantastic. However, one of the biggest things I see when I'm working with companies who are implementing all these new technologies is to keep in mind that, fantasy football is not football. The spreadsheet is not the factory floor. And the real art of doing this is actually taking that dashboard down to the factory floor and talking to people actually doing the work to see how they respond to it, rather than simply shipping that up the hierarchy to the senior executives. And when I normally go onto factory sites, and these can be service operations as well, I look at the dashboards and I look at do those metrics reflect what the operators need to know on the factory floor? And this can be anywhere from manufacturing, even into surgery rooms. They need to know what's happening now and what's going to be happening 2 hours from now. They don't need to know the financial ramifications of someone else's KPI on a monthly basis. So making sure these dashboards actually deliver the right information to the right people at the right time is key. If I'm driving, I don't want to be looking at your dashboard while I'm driving. That's why take the spreadsheet down to the factory floor, ask if we're actually serving the people doing the work. Second problem is we've all heard this term, data is the new oil. Well, we don't want oil all over the place. We don't want data all over the place either, because if we do, we can end up in a dangerous situation like this. This is a tragic event that occurred about 2 years ago at a U.S. refinery. And unfortunately, there were 2 fatalities. Now, the problem is not that they didn't have the right data. In fact, they had so much data that almost 4,000 alarms going off before the disaster. So the information that was needed actually got lost in this abundance of data. So too much data can actually hurt just as much as it could help. And what we really want to do is take this data and turn it into information that helps us reduce risk. So what we're really looking for is leading indicators. The problem with leading indicators is they tell us something we might want to not know about our system, which means maybe we need to invest in maintenance. Maybe we need to invest in training. Maybe we got to shut down for 2 days, right? And finally, if we start to turn data to information and leading indicators, do we have a culture that accepts bad news and uses that to make improvements? So as you'll start to see, a large part of benefiting from AI is actually having a culture that's going to accept data that tells us things we don't want, right? And filtering out data that's not relevant to us at the moment. 3, and this is important, there's the current framing is around industrial AI and all its different forms. I personally think for those of us implementing this into a system, to think of it as a control problem rather than an artificial intelligence problem or challenge. And what I mean by that is we can buy artificial intelligence, but what we're really trying to do is control our systems so that it maintains or grows profit margin while at the same time reduces the risk to the business and the people in it. So we're going to, and why this is also so valuable, it actually tells you which projects we should work on first. So now we have a quantitative way to sequence the problems we're going to solve because it increases the controllability of our system. And just to give you some insight of how the AI community is responding to this, this is Jan LeCun's comments on the left. He's the chief AI scientist at Meta. And you'll see his description of a world model, which is basically a lot of these Gen AI, et cetera, tools. He actually describes it in a mathematical framework, which is actually over 40 years old. That's model predictive control. Now, our objective is not to make you all control experts. However, I'll leave you with this. If you're riding a bike or driving a car, you're actually doing model predictive control. You don't actually realize it. And you'll also know the better model that you have of your driving environment, the faster you can drive safer. And it's that type of analogy you can use for your digital transformation. So let me give you a simple example of applying control theory to a problem that came out of Xerox Park. So Xerox Park is, of course, was funded by Xerox, but it's essentially where the Apple Macintosh was born, which Steve Jobs took advantage of. The chief scientist at Xerox Park was John Seeley Brown. And he flew out from Park, which was in Palo Alto, to visit his corporate colleagues at Xerox in Connecticut. While he was having lunch, he started talking to the copier repairman. And he asked, how do you go about doing repairs? How do you do your diagnosis? And the copier repairman at lunch told him, first thing I do when I go to a company that's got a broken copy machine, I go straight to the trash can and I dump it out. And what's in that trash can? All the bad copies, right? So if you think about that, from control theory, your feedback loop is corrective. So it should basically contain the information of what's going wrong. And this deep insight by this Xerox copy repairman actually put in a very effective feedback loop. The system itself was actually providing the proper data filtered if we cared to look. So the lesson here is to realize our system's trying to speak to us, right? And we help the system by listening to what the system says and creating that corrective feedback loop. And I also want to note that these feedback loops appear in many different forms. They're not simply just typically like wiring and diagrams. They're also the way that we as human beings interact with our colleagues and the system. And just to bring this home as a timeless principle, a key insight from MIT professor Jay Forrester, who founded our system dynamics group over 60 years ago, with this fantastic comment. Most people are unaware of the hidden feedback loops that are controlling their lives. Now, what does this have to do with adopting industrial AI? You and I go out to look at the system, and just like John Seeley Brown, let's look at where these informal, human-based feedback loops formed, understand why they formed, and then think, could some of the new technologies, including data collection, machine learning, data filtering, or other types of AI, including agentic, could actually take that informal feedback loop and turning it into something much more successful. And also to note, we don't have to automate it 100%. Sometimes 80% automation is all that's needed. In particular, the percent of time I spent finding data versus interpreting it is 3 to 1. I spend at least 3 times as much time looking for that information as I do actually analyzing it. So anywhere we can put in tools that gets the information faster to the people that need it is a huge win. Okay. You cannot think about control systems without thinking about time constants. So basically, whether you're a control system engineer and you understand Laplace transforms, or you know how to build a schedule, we all know one thing is you've got to understand the time constants of the system. So what does that mean? When you schedule something, if a task takes 2 hours, you can't schedule it in half an hour, right? And in most processes that I'm in, no one actually knows how long anything takes. How long does it take to set up this machine? How long does it take to change over to move from product A to product B? And how does it vary depending on the product and also the staff? When I usually go into the system and I ask what the time constants are, they'll say, this is a recent example where we needed to do some really critical scheduled maintenance once a week to keep the assembly line up and running. And I asked the question, how long does that changeover take? And they said, it's 120 minutes in SAP. And I said, that's not quite what I asked. I asked, how long does it take, right? How long do you think it takes? And they said, we think it takes about 180 minutes. Okay. So then I asked the question, when are we doing this next? Like Thursday. I go, can we watch it Thursday and measure how long it actually takes? It actually took 270 minutes. So imagine running all these planning and scheduling and forecasting algorithms that are based on the time constants of production or service delivery, and we've got the wrong numbers in there. And why that's critical is we have customers, and our customers are very demanding and they're time sensitive. So one of my clients served Walmart. So Walmart's pretty intolerant of you not completing your tasks on time. So how do we actually go into a company, understand where their time constants are broken and start improving them? We basically use an approach that John Boyd used for a strategy for fighter jets. If your time constant is faster than your competitors, you will win. And he broke up the time constant into 4 steps: observe, orient, decide, and act. So now why that's important is I don't really want to buy AI. I don't want it. I want to buy faster time constants. That's what I want to buy. Now, I can't just buy a faster time constant. It's like trying to buy a hole in the wall. I have to buy the drill. So if you look at what John Boyd did when he broke down that time constant, those 4 steps, observation, orientation, decide, and act, those are all the natural steps that we use in any activity like riding a bike or driving a car or adjusting a machine process. Now, if you look at it, those steps can be pretty slow. Observation means we have to go out and collect data. Well, that's something we can go out and buy. We can buy better observation. Now that we've collected all this data, we can't just throw it at our people and expect them to react to it quickly. We have to basically take that data and turn it into information for a decision. That's the orient step. We can go out and buy online mathematical models and deep learning. So these are things we can all buy. Now, if we do a good observation and orientation, the decision we need to make should be pretty straightforward. So now it's going to speed up our decision process and, thank goodness, reduce the number of meetings we have. And then finally, there's the action step. This kind of goes into the automation and the robotics part of Industry 4.0, but the key is to make sure you get those first two steps on observe and orient correct so that we make better decisions and actions. So let me actually show some examples on these OODA loops. This is actually one of my roles is I teach lean operations in our Leaders for Global Operations program here at MIT. And our students go out and do thesis work. So one of the things that people, in terms of observation that's really important that people aren't really good at is detecting defects and problems in a high-speed assembly line. So this is somewhere where artificial intelligence in the form of visual recognition and pattern detection is exceptionally valuable. And one of my students here was really looking at defects in terms of syringes for the hospital industry. And as you know, we need hundreds of millions of syringes a year, and they have to work every time. So you can imagine the quality problem here is a real challenge. Here's what our student did is when you manufacture these syringes, the defect rate's already really low. It's like 99.99%. But how do you add an extra 2 nines? The challenge is, how do I train a deep machine learning model when I don't have a lot of failures, right? It's very difficult. I can't train on the actual production data because there's very few mistakes in it already. So one of the things our student did was, you'll see that image on the right is one of the defects you have in a syringe is in the rubber plug. So if you look, and that happens rarely, but it can be catastrophic. So what our student did was took an actual example of a defect in one of those plugs. And if you look in the lower right-hand corner, they actually created synthetic data that moved that defect around through the entire plug so that we had training data that we didn't have to generate from actually having thousands of real samples. And the result of this, in that lower right-hand corner, clearly detected at high speed that there was a defect in this syringe that no human could do at this speed. So these are the types of things that are possible. If we can buy observation and orientation, that's a huge value to training these algorithms. So point number 5, there's a lot of work on artificial intelligence, and there's more every day. But one of the things we emphasize is systems are complex. If we can simplify those systems, not only will they become more profitable, they'll also become easier to understand and model. And so that's a principle I've been working on for the past 20 years because I've worked in industry practice. But now our colleagues in the artificial intelligence academic area are coming over to that level of understanding now. So Andrew Ng from Stanford, who's one of the leading luminaries in artificial intelligence, recently published this article in IEEE, Unbigging AI, right? Let's keep it simple. And what is the implication for this group? When you're building a mathematical model of something, and let's take a large language model. Do I really want to build a large language model to accomplish my company's goals when we have very smaller set of language that we use? So I just want to say as an example, like in my own family with my children, no matter what they ask, the answer is no. So I have a very small language model. But what you'll see in this data that was provided by IBM is when you take a generic large language model and you restrict it to your business, you're going to get significantly higher accuracy. Here it went from basically 25%, which is exceptionally low, to 75%, which is actually starting to become practical for use in business. What's also exciting is instead of using 12 billion parameters, you're actually down to 300 million. So that's a 2 order of magnitude reduction in the data you need. So not only does it cost money to collect data, it actually reduces the cost to actually run these models, which is a huge problem in AI. So keeping it small, and why look through the whole haystack when we already know our customers' responses are limited? And this is something reinforced by an industry veteran I talked in, who's in the B2C market for basically digital information. And his comment was, why are we looking at these bleeding edge large language models when we only have 5 products and services? And when you look at customer complaints and errors, for which they were getting like 50,000 a day from phone calls and emails, basically 80% of those problems were 4 to 5 issues. So before we go out and buy these massive technologies that can do everything, let's just focus on the problem at hand. It's a much better approach. You'll sleep better at night, and you'll get faster results to report through the organization. Just a quick example of this. McDonald's, I think, invested north of $1 billion in one of these systems that basically was automated orders taking when you drive up to the window. It had an accuracy of 85%, and that's not acceptable for a drive-in restaurant window where speed is key. It failed their OODA loop. Now, surprisingly, maybe not surprisingly, Popeyes, which is a chicken outlet, actually had a 97% success rate. And you can see why. The menu at a chicken fast food restaurant is actually much simpler than McDonald's. So it was much easier to implement. So before you jump and make the big investment, test this out and realize if you have a lot of different product offerings, you're making it more difficult on your model. This also goes to industrial robotics. So think of the action step. This is MIT's own Rodney Brooks, who's done amazing work on robotics over the past 40 years. In the upper right-hand corner, some of you might be familiar with the Baxter and Sawyer robots. And that was around 2012 era. That company's actually been sold and went basically semi-bankrupt. And Rodney Brooks's new company is that simple robot in the bottom right-hand corner, which actually moves things linearly and rectangularly in your plant, right? So being simple, applying 80-20 is really what it takes to be successful in this industry. And it goes back to Rodney's quote that you see here that, you know, we're overestimating what generative AI can do for us. It can only do parts of things for us. We still need creative thinking as well. Number 6, results are boring. Okay. So everyone gets excited about buying the technology, but when it actually gets implemented, you see the value, people stop caring. So that's a mystery we'll just for another time. But this is an example how I helped a major brewery increase their production by 5%. That's 1 million cases of beer per month. And because the solution was so simple, basically we eliminated 5 hours and 45 minutes of waiting just by diagnosing that the problem was poor information flow. 5 individual spreadsheets on a local laptop and 2 missing pieces of data from the line. We're able to put that up in the cloud. In less than 3 weeks, we're able to see this change. Everyone was excited about it, but the minute the money was banked, they ran on to do something else. And I'm like, as a leader, you really have to keep people focused on what's good for the business and not jump to what's exciting. So, and the other nice thing about this is I think the investment for this was under $10,000. So there are these big wins out there, but are we actually willing to reward small changes that produce big outputs? And then finally, I want to end up with this point that really comes out of our system dynamics group at MIT. It's a new paradigm, which first came out in 1972 by researcher Donella Meadows. And it says, if you want to change a system effectively, you don't change the whole thing. you want to look for its leverage points. And I won't go through, we went through a few of those leverage points today, right? Because 95% of your system you want to leave alone. And you'll notice that she's mentioned here, upgrading your feedback loops, reducing time delays, understanding the rules of the system. And finally, which I put in number 2 here, is we need to think differently about our systems if we actually want to be the winners in the industrial AI adoption game. So I just want to thank you so much for your attention. And before I take questions, I just want to tell you a little bit about our course. So we have a very action-packed course here, October 9th and 10th, here in Cambridge. And not only will I be talking in more depth about applying system dynamics and the technologies, we have some amazing guests, including experts from understanding the whole field of industrial AI and who are the main players, with the LNS CEO, Matt Littlefield. We've got some really exciting of the cutting edge technology that was developed out of MIT's Media Lab, which produces real-time value streams using the most sophisticated artificial intelligence there is today. The CEO, Cyrus Shaul, will be joining us for that. And then finally, Peggy Gulick, whom I've known for over 10 years and is one of the most successful people in starting on the factory floor and delivering results with technology that I've had a part of, is going to talk about her journey. So we're very excited about that. And of course, you'll end up after these 2 days blanking out some space where you can work on your own playbook and also share some examples with your colleagues in the class, so that when you go back to work Monday, you're gonna get to where you want to go faster and in a way that's less stress on your employees. And then finally, Cambridge is a beautiful place to be in October. And of course, there's always going to be surprises. So this was a surprise lab visit we made last time with not only using AI, but additive manufacturing. So there'll be some surprises for you as well. So let me just wrap up, and I'll ask some questions. We're in the results phase now. It was fun with playing with the technology, but now we got to show some money and we got to show some risk reduction. And the winners won't be determined by who buys the best technology. It's going to be who incorporates it faster. And culture, people, and leadership are key. Thank you very much. And Diane, I'll take a few questions if we have a little time.
Thanks, John. We do have a few moments, and we have some great questions. Let's start with, how is the emergence of AI, including agentic and multimodal, affecting Industry 4.0?
Okay, that is a fantastic question. So I think most of us have been doing agentic AI for more than 15 years without knowing it. So for the subgroup here, and probably many here, for those of us that have built macros in Excel and also set standards and templates for people to use, or shot short videos for people to train, which I've been doing for over 10 years, we've already been doing agentic and multimodal AI. However, there still is a lot of handiwork and understanding macros and things like that. So only a few of us have time to do it. What's changed today is now, if you look at some of these fantastic computer algorithms, is especially around no code and low code, you can start building your own digitally driven workflows, agentic AI, without deep knowledge. So that's what I really say is changing. Is the techniques have been around for a long time, but it's more like now we're giving people calculators when before they just had slide rules.
Thanks. Let's do one more quick question. I know we're getting close to time. We've got a couple questions about synthetic data. So let's start with, how do you manage false positives with synthetic data?
So I actually do, when I start looking at false positives, I answer this in 15 seconds. This is a great question. And it goes back all the way to classic statistics. Is the power of managing false positives and false negatives has to do with the quality and precision of the data you collect. So in this example, a great deal of time the students spent was actually making sure the cameras were taking very good pictures and that they were integrated well into the syringes, and experts actually looked at that to make the comparison. So that's how they drove the precision and therefore they were able to get very few false negatives, which made it to be, then it lets you reduce the false positives. And by the way, they track false negatives after they were catching these on the real assembly line. They're always measuring their false positive rate so that they can actually adjust this in real time.
Thanks, John. Everyone, if you'd like to hear more about this and do a deeper dive into these topics, please consider joining John and I at the upcoming course, Strategy, Survival, and Success in the Age of Industrial AI, on campus October 9th and 10th. This program equips strategic decision makers with the essential AI management and leadership skills to drive successful transformation. More information can be found on the MIT Executive Education website. We'll also be sending out a recording of today's session via email to anyone who registered, and there will be more information in that email. Thank you for joining today. Hope to see you on campus. Thank you, John.
Thank you, everyone, and thanks for spending your time with us today.